Welcome back to my series on PixInsight. This is the fourth video in the series, and I was originally planning on doing one on linear processing immediately following calibration. But after a number of questions on calibration, I realised that there is some more to discuss, because not all sensors work the same, and also in recent months a new version of the pre-processing script has been released. So I thought I'd take a look at those and go on to discuss the differences between sensors and how that affects calibration. The key thing about calibration is, while it is a mechanical process, it is a very significant process, especially the integration, and it's a business like rubbish in, rubbish out. If you get this part wrong, it doesn't really make your life easier when you come to try and process the image later on. So under the script menu, there is under batch processing, there's the batch pre-processing script which we looked at in the previous video, and at the bottom is something called the weighted batch pre-processing script, which has recently been added. If we bring that up, it looks very similar to the one that we used in the last video, except for a new section, and that is subframe weighting. Now, in the previous video, I used something called the subframe selector to produce a weighted goodness number for all the frames, and I used that goodness number to basically decide if some of my frames should be completely discarded. Here, what it does is it uses the same algorithms that are used in the subframe selector to give a goodness value, but here what it does is it just simply changes the contribution of each file to the final stack through the processing sequence. So all the other parts of this are identical. What does happen here though is that there's this section here on subframe weighting, and there's three options depending when you do the subframe weights, and they can be used at various different combinations. So you can have that combination or that combination or that combination and so forth. So what is probably the easiest one to start off with is to generate subframe weights. Do not compute the weights after registration, and then use the best frame as a reference for registration. So what it will do there is it will select typically the one with the best star shape and size. If you look at the weighting parameters, there are four weighting parameters. There's full width half max, which is the star diameter, eccentricity, and the signal to noise ratio, and then there's the pedestal weight. So you can alter these in any combination and it'll give you a slightly different result. And what they've provided is three presets. One for nebula, which basically says I don't care too much about stars, but I do want good signal to noise ratio. One for cluster, which is very different weighting, so it puts far more emphasis on star shape and size and eccentricity and less on signal to noise ratio. And there's one on galaxy, which is somewhere in between. So to save time, I reran the sequence of images that we looked at in the last video, and I chose the cluster subframe weighting, which should give me good star sizes. I ran it and it created another set of calibrated files and an image stack, and in true Blue Peter fashion, for those of you who lived in the UK, here's one I prepared earlier. So if I look here, this was the original image I produced, and this was the second one I produced using the weighted script. Now, one of the things that, a little trick I'll show you, when you have big images like this, they tend to occupy the screen rather a lot, and you want to zoom in and you want to see the same part of each image. So what you can do here is you can zoom in. So let's zoom into this central part. And if you want to see exactly the same part of the image on the other one, what you do is you drag this tab on top of the other tab, and you get a window shape pop up by the cursor. And when you release it, you now have equivalent views on both your images. And when you compare the two images side by side, they are very similar. Now, these have been stretched because you can see the little green bar down the side. A more scientific way of determining whether the actual picture is better or not is to look at the process console, which when you actually did the analysis, it comes up with a set of values. So if I scroll back to when I last did it, it has Gaussian noise estimates, signal to noise ratio estimates, and so forth. These are a more scientific way of measuring the comparative performance of the two scripts. And in fact, interestingly, I noted the two versions down, and while there's three values, one for red, green and blue channels, it actually improved the noise of the green and the blue channels and slightly worsened the noise of the red channel. And there's a reason for that, which is the emphasis on the weighting was for star shape and size, because I chose cluster. I'm assuming that if I chose nebula, that the red nebulosity in this image would have a slightly better signal to noise ratio if I'd chosen that option. Okay, if I look very closely at this star, these stars are slightly better in this one than in this one. There's slightly less colour artifacts around the side, but it is very slight. And the numbers that I got of both sets of integrations were pretty similar. On some other test cases, there may be more distinct differences. In this second part of the video, I'm going to take a look at some of the interesting problems that occur when people use the latest CMOS cameras. You've got to realise that the pre-processing script is running a mathematical algorithm behind the scenes, and this is taking bias frames and dark frames and subtracting them from light frames, normalizing them with flat files, and then registering and then averaging them all before coming out with a result. And we don't necessarily need to know everything that's going on behind the scenes, but the assumptions that these are based on are historical and based on typically CCD cameras that are being used by astrophotographers from like 5 to 10 years ago. And what's happened is the more recent CMOS sensors in particular have started to change the way the sensors work, and it conflicts with the way that we want to calibrate an image. And let me give you an example. So if I exit this script and bring up a file. So when I open a file with Sequence Generator Pro, it only shows me the image area of the sensor. If I do the same image with something like the SkyX using a different driver, you can see that this image has got a black margin around the outside. And what this is an area on the chip that is physically masked off from the light. So the sensor can see what's light and what is dark, and in an attempt to try and make the most of their image quality in traditionally consumer cameras, it does a very basic form of dark subtraction. So it looks at the mean value of all the dark pixels around the margin and it subtracts it from the image. And clearly, as the length of the exposure increases, this becomes lighter and lighter and it subtracts it from the image. Now, why is that a problem? Well, in the calibration system, there's some equations, and I've made myself some notes to help explain. So if I just bring up a little frame. So what happens is, traditionally, you take dark frames that are similar to the light frames in terms of duration and temperature. That's easier said than done with a traditional consumer camera, because you typically do not have any control over temperature. And because you want to compensate for those minute differences between the light frames and the dark frames, in the calibration process there is an equation, and within that equation is something that looks like this, where you have a factor times the master dark minus the master bias, and that is a number that's then used in the calibration process, but it assumes that the dark value is bigger than the bias value, which gives you a positive result, because all it's doing is measuring electrons. So you can't have negative electrons, you can only have positive electrons, as it were. I know electrons have negative charge, but don't go there. Anyway, so on a CMOS camera, because of this dark subtraction that occurs, and it's differing amounts on differing chips, what happens is they internally semi-compensate for the dark current, and in a cooled camera you get the condition where this part of the equation takes a big bias frame from a small dark frame. In other words, the mean value, the average value of the bias frame, which is the very short exposure with the lens cap on, is actually higher than the one that may be 20 minutes long. And that's obviously a negative number, and that completely throws the equation. it not only throws the equation, which means that when you start to do the calibration process, it creates black pixels, but also there are other things that go on a CMOS sensor, things like amp glow, where the amp glow skews what it thinks is the dark subtraction that it does internally, and it overcompensates. So this can really occur. And one of the best papers on it shows that with the popular Panasonic 4/3 chip that's now finding its way into Astro cameras, this occurs, and the overall mean value of the frame decreases with time. So what's the solution? Well, the solution is match your dark frames to your light frames for both duration and temperature. The more accurately you do this, the better you can get your calibration, and you don't then need to use this factor that's in there. So that means if it's measuring amp glow, it will subtract all of the amp glow, 100%, not 90, not 110%, and it should remove the amp glow from your images. The other part is calibrate your flat frames with just a master bias only. Don't do master bias and dark, because otherwise you get this subtraction again. And that's assuming that the flat files are all using short exposures where the dark current hasn't any effect. And then finally, when you calibrate your light frames, you only calibrate them with the master dark and the master flat. You don't use the master bias again. We've avoided the situation where we're subtracting biases from darks and factorizing them, and we're also avoiding any situation where we subtract a bias from a dark. And what that means is that in the calibration scripts, you may find if you have strange results and you're using a CMOS sensor, you may have to abandon the script and do your calibration separately using the process tools themselves. So I'm going to shut this down for a second and bring up some suggested settings for the calibration tools that avoid this problem on a CMOS camera. Right, now in the very first video I suggested a novel approach to remember settings on process tools, and that is by minimizing them, as I've done here on screen, and then saving them as a project. So this is a project that I've named Calibration, and I've got two groups of tools. I've got a group up here which is to do with CCDs, and I've created a group down here which is slightly modified for CMOS sensors. So I'm going to pull each of these up to show you what the key parameters are and which ones to use for CMOS and CCD. So the first one is regarding the creation of the master biases and darks. Now if I remember rightly, there's not much difference between either CCDs or CMOSs, but what you're doing is you're combining them with average, with no normalization, there's no weighting, and there's no normalization, and you're doing a very simple sigma clip. So in other words, if there was something like a cosmic ray hit, it would remove it, but nothing too intelligent. So that's pretty straightforward, and those settings you would use to create your master bias and master darks for each of the times and temperatures that you're using. So the next one, which is more important, is the flat calibration one, and this is where the changes start occurring. So for a CMOS camera, you typically either use a master bias, and you'd locate your master bias file and put it in here. You do not put the word calibrate in, that you leave that alone. Or if you have a dark frame that's exactly the right duration as your flat frames are, you can alternatively use a master dark of the right temperature and duration as your flat frames. That typically might only be a second or two, so for practical purposes the bias files are absolutely perfect. And that's how you would calibrate your flat files before they get averaged. So then we have the flat averaging or integration, which is the posh word for it. Here you're doing averaging, you're multiplicative in its normalization, because sometimes, especially with things like sky flats, they might be slightly different. You're using the same weight on everything, and you're just doing a simple pixel rejection. Anything over 15 samples I use Winsorized Sigma clipping, and with scale and zero offset on the normalization. So nothing particularly fancy about that, very similar settings as you would use for a CCD. It gets a little bit more interesting when it comes on to the light calibration. This is where another significant difference is. So This is light calibration for a CMOS sensor. So I haven't got overscan on my images, so I don't need to worry about this. I do not enable master bias, but I do enable master dark. I do not either calibrate or optimize it, and I do use a master flat. So in these empty boxes here, you would pull up your master flat file, so wherever it is, and so forth. Now, if I compare that to the same one here, this is the CCD calibration. The CCD calibration has bias and darks enabled because it can do that scaling factor, and it's got the word optimize there. So in other words, if your CCD, either the time or temperature of your dark frames isn't quite right, this little button here, along with biases and darks, will get a good result. So subtle differences between the two. Now, moving on, we've looked at light calibration. The next step would be debayer and register, and then light integration. So debayer is straightforward. It's basically a list of files with the order of the RGB sensor, all the different sequences of red, green, blue, mosaic, or you can put it on auto if it's reported in the file itself. If you're using a Fuji camera with an X-trans sensor, it works it out for itself. And then registration, which should be similar for both. Again, you'd pick up a reference image, which is probably the one with the smallest stars, and so forth. This star alignment module is far more sophisticated than the one in the batch preprocessor, and it does allow you to modify the star detection and matching. So if you have high degrees of noise and so forth, you've got various options here that you can cope with that. And then finally, the light integration. So again, at the top you'd have all your images, so we can get rid of them. And here you'd have your combination method, which is averaging. Normalization is additive with scaling because we don't want to multiply these images at all. And you're using noise evaluation. There's other evaluations as well. Noise evaluation does it for me. And then in the rejection, again, another one of these statistical rejectors, and the parameters, I normally start with something like 3 or 4 sigma, low and high settings, and so forth. So those are the settings I would use for the individual tools with a CMOS camera. There's one thing left to discuss, and that is the cosmetic correction. I'm just going to pause for a second and bring up some images and show you how you apply cosmetic correction. I've loaded up the screen with a very challenging image of the Squid Nebula. Yes, it's there in the middle of the screen, the very, very faint 03 narrowband file that was a 1200 second exposure with 2x2 binning on a quite noisy CCD. If I do an image stretch, you still can't see it. If I do image invert and hit image stretch again, you can just about make out the phallic shape of the Squid Nebula there, but it is incredibly dim. Anyway, I don't really need it inverted at the moment because I want to see the hot pixels, and this is what I'm going to correct with the cosmetic correction tool. I've been playing with this a little bit and I found the dark file that matches this. So this is 1200 seconds 2x2 and it's going at -20, and I managed to find the master dark file that corresponds to. And what you do with cosmetic correction is you hit the real-time preview button and you get an enlarged view. And what we're going to do is take out the pixels. So if you look very carefully, you may just be able to notice that as I drag the hot pixels slider down, that the hot pixels start to disappear. So as you drag it down, there's a sigma readout. It tells how many pixels it's removed. I normally around about the 3 sigma level. So it's taken out 4,500 hot pixels. And you can do the same for the cold pixels as well. Something around the 3 sigma is normally quite a sensible one to do. And having done that, you've kind of done the job. Although if you want to, you can do auto detect. And so for instance, if your dark files are a little bit out of date and more pixels have occurred, you can additionally enable these two, and you can also see if that has any effect of removing more pixels. A couple of pixels change, but not much, so I'll leave that there. Okay, so with that done, with those settings on cosmetic correction, I can close down the preview. In fact, I can close down this image as well. And what I'm going to do is drag the cosmetic correction icon to my desktop, and it's come up with a process name. So I'm just going to call it CC Squid. And I can close this down. Now what happens is, we were looking at the pre-processing script before. So on the pre-processing script, either one of them, there is a tab for cosmetic correction. If you hit apply, you can now select CC Squid and it'll apply it in the calibration process. So it will remove the hot pixels and replace them with neighbouring pixels. And that's how you would use it with the script. If you want to use cosmetic correction with the separate processing tools, you get a hint from this window how it is applied and where it's applied. So it's applied before debayer and image registration, which makes some sense. You want to replace pixels with calibrated pixels, not uncalibrated ones. So if you exit out of here and open up your cosmetic correction for the Squid Nebula, what you need to do is add your Squid files. So here's my calibrated files, and they're ending in a C, which means they're calibrated. So scroll down, and these are my oxygens. With all the calibrated files loaded, I would then hit apply, calibrate oxygen files, which would create a further set of files with the word CC after it, standing for cosmetic correction, and then those files would go on to be registered and integrated, or if it's a color file, color camera, it would be debayered, registered and integrated. So that's how you apply cosmetic correction. And I think that's enough for calibration for one day. Thank you for listening, and I will definitely get on to linear processing in the next video.